Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. The solar system's hidden gems. A look at dwarf planets. For generations, our solar system seemed like a well-ordered family portrait. Planets, neatly categorized by size and composition, circled the sun in a predictable dance. But this seemingly stable picture was shaken with the discovery of distant, icy worlds that blurred the lines between planets and asteroids. Enter dwarf planets, a fascinating class of celestial bodies that hold a unique position in our solar system. They share some characteristics with planets, like being large and roughly round, but lack a crucial feature: dominance in their orbital neighborhood. Let's explore the world of dwarf planets, exploring their properties, the ongoing debate surrounding their classification, and the exciting possibilities they hold for furthering our understanding of the solar system's formation and evolution. The dominance debate. Defining a dwarf planet. The key distinction between a planet and a dwarf planet lies in a concept called orbital dominance. A true planet is the gravitational heavyweight in its orbital zone, clearing its path of most other objects. Imagine a powerful king ruling his domain. That's essentially what a planet does in its orbital neighborhood. Dwarf planets, while sizable, share their orbital space with a crowd of celestial neighbors, such as asteroids or even larger planets. This lack of dominance, their inability to become the sole gravitational ruler of their orbital territory, relegates them to a separate category. However, the line between dominance and sharing isn't always clear-cut. Some dwarf planets have eccentric orbits, meaning their path around the sun isn't a perfect circle but rather an oval. This eccentricity can sometimes lead them to temporarily dominate their orbital zone, further complicating the classification picture. The ongoing debate about dwarf planets reflects this complexity, with some astronomers arguing for a more nuanced approach to their categorization. A celestial zoo. The diverse landscape of dwarf planets. The realm of dwarf planets is surprisingly diverse, defying any attempt to paint them with a single brushstroke. Some, like Pluto and Eris, are icy worlds, harboring potential oceans beneath their frozen surfaces. These distant cousins of our own icy giants might hold hidden reservoirs of liquid water, raising intriguing questions about the possibility of life existing in such extreme environments. Others, like Ceres, the largest dwarf planet in our solar system, are more akin to giant asteroids, with rocky compositions and a lack of extensive atmospheres. This variety highlights the complex formation processes that shaped the early solar system and the ongoing quest to understand how these celestial bodies came to be. As we continue to explore and study dwarf planets, we gain a richer picture of the diverse building blocks that make up our solar system. A world of ice and mystery. The composition of dwarf planets. Dwarf planets, residing in the frigid outer reaches of our solar system, are predominantly composed of ices like water, methane, and ammonia. These ices likely condensed from the swirling disk of gas and dust that gave birth to our solar system billions of years ago. Imagine a cosmic snowstorm, where these frozen molecules clump together under the influence of gravity, eventually forming the icy cores of dwarf planets. The presence of these ices raises intriguing questions about the potential for hidden oceans or subsurface water reservoirs on these distant worlds. Studying the surface features of dwarf planets can offer clues about their composition. Pluto, for instance, boasts a heart-shaped feature rich in nitrogen ice, while its dark plains hint at the presence of methane and other volatile compounds. These variations in surface composition suggest a complex internal structure and potentially even past geological activity on some dwarf planets. As we develop more powerful telescopes and spacecraft, the ability to analyze the spectral fingerprints of these distant worlds will provide even deeper insights into their icy makeup. A thin veil. The atmospheres of dwarf planets. Some dwarf planets, like Pluto, possess thin and tenuous atmospheres composed primarily of methane gas. Imagine a wispy fog clinging to the surface, barely clinging to the dwarf planet's weak gravitational pull. These atmospheres are thought to arise from the sublimation of ices on the dwarf planet's surface, where frozen molecules transform directly into gas due to the frigid temperatures. As Pluto approaches the Sun in its elliptical orbit, the increased solar radiation can trigger a temporary thickening of its atmosphere, revealing fascinating seasonal changes on this distant world. Studying the composition and behavior of these tenuous atmospheres offers valuable insights into the volatile history of dwarf planets. By analyzing the abundance of different gases and their interactions with solar radiation, scientists can piece together clues about the internal composition of these objects and the potential presence of volatile reservoirs beneath the surface. The faint atmospheres of dwarf planets, though seemingly insignificant, hold valuable secrets waiting to be unlocked. A celestial dance. The orbits of dwarf planets. Dwarf planets, like their larger planetary cousins, follow paths around the Sun. However, their orbits often deviate significantly from the relatively circular orbits of the 8 planets. These eccentric orbits can take them on wild journeys, bringing them closer to the Sun at some points and hurling them out to the distant fringes of the solar system at others. Imagine a comet streaking across the sky, but instead of a burning tail, it's a dwarf planet following a highly elliptical path. The eccentricity of dwarf planet orbits can have a profound impact on their environments. As a dwarf planet swings closer to the Sun, the increased solar radiation can trigger changes in its atmosphere and surface features. Conversely, the frigid expanse of the outer solar system can cause these worlds to become locked in a deep freeze. Studying the orbital characteristics of dwarf planets sheds light on their past interactions with other celestial bodies and helps us understand the complex gravitational dynamics at play in the solar system. A celestial entourage. The moons of dwarf planets. Just like some planets boast their own moon companions, several dwarf planets have their own fascinating moons orbiting them. Pluto, for instance, has a captivating system of 5 known moons, each with unique characteristics. Charon, Pluto's largest moon, is even close enough in size to be considered a dwarf planet itself in a double dwarf planet system. Studying these moons can reveal valuable clues about the formation history of the dwarf planet system and the potential interactions between these celestial bodies. For example, the analysis of the surface composition of Pluto's moons suggests they may have originated from a giant impact event billions of years ago, with debris from the collision coalescing to form the moons we see today. Additionally, the presence of potential water ice on some of Pluto's moons raises intriguing questions about the possibility of subsurface oceans or even cryovolcanism, where erupting ice volcanoes might have shaped the moon's landscapes. A window to the past. Dwarf planets in the early solar system. Dwarf planets, with their relatively pristine surfaces, are considered relics from the early solar system. Unlike the 8 planets, which have undergone significant geological changes over time, dwarf planets have remained largely unaltered. Studying their composition and structure can offer valuable insights into the processes that shaped our solar system billions of years ago. Imagine a cosmic time capsule, frozen in time, holding clues about the swirling disk of gas and dust from which the solar system formed. Analyzing the abundance of different elements and isotopes in dwarf planets can help scientists reconstruct the composition of the protoplanetary disk. Additionally, studying the distribution of ices within dwarf planets provides information about the temperature and pressure conditions that existed in the early solar system. By piecing together these clues, we can build a more comprehensive picture of the processes that led to the formation of planets, moons, and other celestial bodies. The Pluto Saga, a reclassification and its ramifications. The discovery of Pluto in 1930 initially classified it as the 9th planet in our solar system. However, the subsequent identification of other icy objects in the Kuiper Belt, a region beyond Neptune, sparked a debate about Pluto's status. As more and more objects with similar characteristics to Pluto were discovered, the question arose: could they all be considered planets? In 2006, the International Astronomical Union, IAU, made a controversial decision. To bring order to the growing number of objects beyond Neptune, they established a new category: dwarf planet. Pluto, along with other celestial bodies like Eris, was reclassified under this new category. This decision, while intended to provide a clearer classification system, was met with mixed reactions from the scientific community. Some astronomers argued that Pluto deserved to retain its planetary status, highlighting its historical significance and unique characteristics. A universe of possibilities. The future of dwarf planet exploration. Dwarf planets, once relegated to the fringes of our solar system, are now targets for ongoing exploration. Missions like New Horizons' historic flyby of Pluto in 2015 provided unprecedented data on these distant worlds. The close-up images revealed a surprisingly complex and dynamic landscape on Pluto's surface, with mountains, glaciers, and even potential evidence of past geological activity. As technology advances, future missions aim to explore other dwarf planets and their moons in even greater detail. Spacecraft equipped with sophisticated instruments could analyze the atmospheres, study the surface features, and potentially even search for signs of past or present life on these intriguing objects. By venturing further into the realm of dwarf planets, we unlock a treasure trove of information about the formation and evolution of our solar system, and perhaps even discover new possibilities for life existing in the most unexpected corners of the cosmos.